Hello my dears, today we are going to discuss about the transient stability concept. So in the last classes we discussed about the steady state stability, so in which we gave a small disturbance and we analyze the system, right, and the system itself will adjust to the disturbance and regain its stability. That is called the steady state stability, and by using the swing equation we analyze the system and we find what happened to the rotor and all right. So basically the swing equation is the governing methodology for the steady state stability. But in the case of a transient stability we are using another method we will discuss later now. And what do you mean by the transient stability? So transient stability is nothing but, my dear, what the stability analysis of a system when it is subjected to large disturbance. So what do you mean by the term transient stability? So transient stability is nothing but, my dear, whenever a system is subjected to a large disturbance, my dear, and that also the large disturbance, the magnitude wise, see, the impact of the disturbance will be very high as compared to the steady state stability, steady state disturbance. So the stability analysis of a system when it is subjected to large disturbance is called the transient stability analysis. So what are such disturbances, large disturbance? What are the examples of such large disturbance in the power system? See, one of such disturbance is nothing but, my dear, dead short circuit. See, dead short circuit. Suddenly 2 or 3 phases of a transmission lines are short circuited. See, that is also a type of a transient disturbance. And another is contingency. So contingency is nothing but, my dear, sudden removal of equipment or loads from a power system. This is called the contingency. So these are the two main reasons for the production of transient in the power system. So how can we analyze the system when the disturbance, when the power system is subjected to such a type of disturbance? So we are using equal area criteria for the analysis of transient stability. This word is very, very important, my dears. As a one-word question, it will be directly asked in the examination. Equal area criteria. As a one-word question, you may expect a direct question from this word, equal area criteria. So, swing equation is for the steady state stability, while the equal area criteria is for the analysis of transient stability. What is meant by equal area criteria? And we will discuss in the preceding lecture. Continuing lectures. No, don't worry. I will discuss very clearly. I will go to discuss, and we have to make some assumptions. Before we are dealing. We have to make some assumptions in transient stability analysis. See, my dear, actually how can we analyze the system means we have to consider the system as a worst system. it is called the worst analysis. It is called the worst case analysis. Worst case analysis. It is known as the worst case analysis. So what is meant by this worst case analysis is that we have to nullify the factor which aids the stability. So worst case analysis means what? Means we have to nullify those factors which help stability. That's the correct word. Aid helps stability. So worst case analysis is actually we have to done for the analysis purpose of the transient stability. So what is meant by this worst case analysis means we have to nullify all the factors which help stability of a system. I will explain one by one so the picture will be more and more clear. Okay. So the first assumption is neglect saturation. Neglect saturation. That means saturation means what, my dear? There will be a relationship of field current is directly proportional to EF. That means whenever we are increasing the field current in the rotor or the salient pole or cylindrical alternator, any alternator, what happens? The induced EMF EF also increases. That is the main thing, because the induced EMF equation is nothing but E is equal to 4.44 into F of phi into N1 number of turns or turns per phase. So whenever we are increasing the field current, normally what happen? There will be an increasing the EMF, and up to particular point this relation will be hold true, and after that there will not be any increasing the field EMF, even though if you are increasing the field current. That point is called the saturation point. Okay, so actually saturation point, if we included it, that means if you are considering an alternator at or when it is saturated, or the point of saturation, also we included in the consideration of this analysis, then the point of saturation is actually what, my dear? At a particular point after, even if we are increasing the field current increasing is a type of change in input. Even if we are increasing the field current, there will not be any change in the output, is the term corresponding to the meaning saturation. Correct, na? Even though we are increasing the field current, there will not be any change, means that system is in saturation, or the field got saturated, the field got saturated. So what is the demerit of if we are including the effect of saturation? Even if we are increasing so many field current, I mean so much of field current, so much of field current, what happened? The system, it aids the stability, na? Did you get what I am meaning? The worst case analysis is the technique we are used to find the transient stability. So before we are moving into transient stability consideration, we have to nullify all the factor which helps the stability of the system. See, so first thing, neglect saturation. We don't want the saturation effect. Saturation effect we don't want means IF will be directly proportional to EF for all the time, as long as or as far as we increase the field current, there will be an increase in the induced EMF. Then only we get the worst case, na? If you are increasing the field current, there will be saturation, means even if you are increasing the field current, there will not be any increasing field current, means it is got saturated. So under saturated condition, can we get a real impact of increasing field current in the output type. What happens in the output? Can we get? No, because the core got saturated. So that is actually a safe zone for us. We don't want to bother about the field current after saturation, because I am very happy. I don't want to analyze anything but after saturation. It is a safe zone. It is a safe side for the analyzer. It is a safe side for the person who analyzes the power system. Is it good? No. We have to take the worst and worst cases, and we have to analyze, and we have to find the stability criteria of what? The system. So if you are including the point saturation, it is actually a comfort zone for an analyzer, so that even if after some point of time, even if you are increasing the field current, the field EMF doesn't change. So I am very happy. I don't want to analyze more. That is a comfort zone. That is actually helps the stability of the system. That's the factor which helps the stability of the system. This is an easy way I can understand. I can explain. Okay. So next point is, next assumption is that these are all our assumptions, my dear. So next assumption is that neglect saliency. Neglect saliency. See, my dear, the power equation of a salient power alternator is nothing but, my dear, EV divided by XD plus V square by 2 into 1 by XQ minus 1 by XD. Okay, this is the equation of a what? Salient pole alternator output power. Okay, if you are looking sine 2 delta, okay, I will write once more. P is equal to EV divided by XD into sine delta plus V square by 2 into 1 by XQ minus 1 by XD sine 2 delta. So this is the equation of what? The power output of a salient pole alternator. What is the problem in this power? If we are take it for the analysis of stability, is there any problem? Let's check that. So what will be the graph which is showing the maximum power versus del? See, my dear, for a sine delta this will be, okay, for a simplified version I will show you. For this term EV divided by X into sine delta, this will be the power. This will be the power. Okay, and this will be maximum at del is equal to 90 degree. Okay, is there any doubt? No. So this is nothing but the P max. PM1, let be PM1. And the next term now sine 2 delta is there, which means this will be the term corresponding to the second term, that is the sine 2 delta factor. Okay, let be this is PM2. Okay, this combined effect will be, see, in this half cycle both will be added now. Both will be added, and like this. This will be the combined effect. This will be the combined effect. This will be the PM. So what happened in the overall output power of a salient pole alternator? See, my dear, the presence of one sine delta term will produce a waveform like this. The presence of sine 2 delta form will produce a waveform like this. The combined effect will be higher. That means P max will be higher than PM1, higher than PM2, which means here you got the maximum stability limit. Maximum stability limit. Stability limit. That means if we analyze the system while considering the saliency of an alternator, we got a power which is very higher. The output power will be very higher. If the output power is very high, means Very high means it is like a sort of simple example I will show you. It is like an ocean. Suppose an ocean, if we pour some water or if you pour some tons of water into a big ocean, is it disturbed? No. Is it clear? But if we add one more glass of water into a bucket of full, water which contain full, a bucket containing full of water, if we add a glass of water to the bucket, it will be disturbed. That is a simple method. See, if the power is very high, the power is huge, means we can't notify the disturbances. We can't see the disturbances in that. But if the steady state limit, maximum, this is the word is very very important, my dear, maximum steady state limit, stability limit is lower, then we can easily see the system. What happens when a small disturbance is given, or what happens if even a big disturbance is given, we can easily see. We can easily see that. But if the stability limit is very very high, means it can accommodate very huge amount of power, means even if a kilowatt range of power, or some wattage range, high wattage range of power cannot be easily visible in the whole big the stability power limit. Is it clear? Is it clear? So it is like an ocean. Even if a very ship is sink in that ocean, the ocean will not be disturbed, will not be disturbed. And even if you pour some glass of water into a bucket of water which is full, that system will be easily disturbed and you can observe. Okay, so that is the concept. So if you considering the saliency, the power will be higher, it is actually helps the stability of the system. But we don't want that. We want the worst case analysis. So we always neglect the saliency while considering this transient stability analysis. That's all. So that was the second assumption. Next assumptions. Next assumption. Neglect damping. Neglect damping. If you are considering damping, so what is the function of damping, my dear? Damping is used to suppress the oscillation. Am I right? Dampings are used to dampers are used to suppress the oscillation. So oscillation is actually a disturbance now. If we are using dampers, then how can we analyze the system in worst manner? Because dampers are there to suppress it actually helps the stability now. So whatever the factor which helping the stability of the system, we should avoid for the analysis of transient stability. So the dampers are actually helpers for the power system, which damps the oscillation produced in the system. So for us in the sense, for the worst case analysis of a system, are dampers are really useful? No, we have to avoid that dampers, or so neglect damping. First one. No damping resistors are used. No damping resistors. No damping resistors. See, my dear, the time constant tau in an RL series circuit is that tau is equal to L by R. If R is high means tau will be very less. Tau is nothing but time constant. If the time constant is very less means the system quickly come to stability. If the time constant is very large means the system will take long time to attain a steady state value. So for the analysis or the worst level of analysis, what we should have we a very big value of the time constant tau or very low value? We need a very high value of time constant. Then only the system will take so long time to be settled. If the system is suddenly settled means it actually helps the stability, right? If the system is suddenly settled means what it is indirectly meaning, it helps the stability of the system because it's quickly settled down. Even if some disturbance happens, even if some dampings, oscillations are happen, it is quickly settled means that time constant will be very less. But if the time constant is very high, it will not set quickly. It will take long time for the settlement. So we always prefer time constant to be high. We prefer tau should be high as possible. For that R should be low. R should be low. That means the R should be minimum or simply 0. Then only tau will be infinity. If tau is infinity means there you get the worst case of the disturbance, because there is nothing for settle. That settle time is infinity means the system will not settle at all. Even if we produce some disturbance in the system, that disturbance will be throughout the analysis. That disturbance will be with us for the full analysis time. So that is very helpful for analyzing the system in the case of transient stability analysis. I think you got the point, right? So now no damping resistors. Next assumption is normally frequency is constant. Frequency is constant. Okay, that's no need to explain, simple. Frequency should be always constant because we are analyzing a system, our transmission line system. Frequency is not that much variable. Frequency is not that much variable. So frequency is almost constant for the transient stability analysis. Because frequency is not a constant means there will be some effect of inductance will come. If there is some inductance will come, suppose frequency is very high, you imagine frequency is very high, what happened? There will be factors associated with the inductance will come into play, capacitance will come into play. So there will be again some things which aids the or which helps the stability. So that we need frequencies constant, almost constant. So we can, okay, no need to explain that now. Frequency is constant. Next one, avoid or simply deactivate automatic voltage regulators or AVR. So what it means, my dear? Actually, automatic voltage regulators are there in the system in order to regulate the voltage. That means in the transmission line there may be so many factors which reduce the voltage. So many factors. There are so many factors which reduce the voltage. So the voltage profile should be maintained in a very good manner. So in order to maintain the voltage profile, normally what we are doing, we are doing automatic voltage regulator. It is type of compensation actually. It is a type of compensation where we are using capacitors or inductor in order to aid or suppress some voltage disturbance in the system. So automatic voltage regulators are actually the helping factors of stability. They are stability helping factors. So for the worst case analysis, we have to avoid that. Simple. Next assumption is deactivate speed governor. So what is the function of speed governor, my dear? Even if you are increasing the speed or decreasing the speed of the system, or the automatically some factors which increase or decrease the system speed, I mean alternator speed, then the speed governor, it will sense the speed change and it will tend or it will help the system to bring back to its original speed. Or in other words, if the load demand is high means the alternator will suddenly decrease its speed, because it can't provide that much electrical energy, because its mechanical energy is not that much, it is constant now. So if the electrical demand is very high means the alternator speed will reduce it. So the speed governor will sense it. Even that means when it is decreases from its synchronous speed, the speed governor will sense it and it will either increasing the input mechanical power, or it will increase the mechanical input in one way, as it will increase the fuel input. No? If you increase the fuel input of a mechanical shaft or mechanical system, what happen? The mechanical energy will be higher, so that the requirement of the increased electrical energy will be matched. Like that, the speed governors are actually the helping mechanism for stability of the system. So if the speed governors are there, we won't get the worst case analysis. We will get a very good case, very stable analysis factor. So we don't want that. So normally deactivate the speed governors. Okay. So these are the very important assumptions before we are going into what the transient stability analysis. Thank you.